Hey, Teresa.
Sorry, I had to unmute it. How are you?
No problem. How you doing yourself?
Pretty good. All right, so I guess I had some questions about this math stuff.
Okay.
The beginning of the book was like, I was like, oh, this is kind of easy. It's pretty easy stuff to memorize. But now I'm like, oh my God, it sounds like gibberish. What am I reading?
Gotcha. The good news is I try to usually only have maybe out of a 20 question test, I might only have two that quote unquote require you to do some kind of algebra or arithmetic type stuff.
Okay.
Well, not arithmetic, but at least algebra. So you
Okay.
shouldn't have too much problem with that. That's also why I make all the practice tests available ahead of time so you can see how many questions are just conceptual as opposed to mathematical.
Right.
If you're not getting all the math, it's probably not even going to necessarily bring you out of an A category instead of a letter B or C
Okay,
per grade.
okay, good. Because I'm like, I'm going to school for sonography. I'm like, oh, should I rethink this? I'm like, what's happening?
No, no, no. You definitely. In fact, you're going to be way, way more prepared for for ultrasound tech or any of that kind of stuff from taking this class because we're going to
Okay.
cover waves and stuff like that, which is critical to ultrasound physics,
Okay.
that kind of thing.
Okay, perfect. All right, that sounds good. I guess I need to be better at also time management too and taking like notes, and I started taking notes, but
Hmm.
like flashcards and stuff. I mean,
Right.
what can
Well,
you really recommend for me to memorize this book and not the whole book?
yeah, what I tell my students, and I write this sometimes in my syllabus and stuff like that. When you're reading, you want to be interactive with a book that you're reading in the sciences, anyways. I mean, I
Mm,
imagine it would help in every realm if you're being interactive with it, but sometimes it can be distracting. But in the science world, when you open a book to a certain page, sometimes that whole page is all relevant, important information that you need to memorize. But most of the
mm,
time, you look at a paragraph and maybe one sentence out of that paragraph or one sentence out of four paragraphs tells you the new concept. All the rest is us providing examples
okay.
of when it works or examples of how it doesn't work and stuff like that. So if
Okay.
you can sort of try to read with that mindset and try to predict particular examples after the author talks about a specific physical principle. See if you can think of a real physical thing that you've encountered that either contradicts or supports the claim. And
Okay.
if you ever find one that contradicts, then you ask me if you can't find the reasoning for it in the book or something like that. Doing that while you're reading will help a lot. And sometimes I've always leaned towards reading way slower, so I read notoriously slow. For instance, read a 1,200 page book one time. It took me 4 years to read it. So
Well, that's a long book too.
yeah, and that wasn't even the War and Peace one. That was way actually considerably longer than when I read War and Peace. Uh,
Yeah.
this one
I
was
have
a,
a
a
I have a bad
biography of
habit.
somebody.
Right. I have a bad habit of letting the audio go and not actually reading it.
I'm not sure. I'm not sure that's a bad thing, to be honest with you. I know it doesn't impact your brain as well when you're not reading it as opposed to listening to it.
Right.
But I would bet that if you listen to it three times, that would be every bit as valuable as reading it really well one time.
Okay.
So
Okay.
don't feel too bad about that. I know that the reading that happens when it reads for you, it's not that energetic and stuff like
No,
that.
no, I know. And then I'm just getting off of work, so I'm like, oh my God, my brain.
There's a lot of the things we ask for math. You mind if you have a second so I can pull
Yeah.
up my iPad? I'm going to
Yeah.
turn on my iPad and show you some typical ways we deal with equations in conceptual physics. So
Okay.
it'll take a second for my iPad to turn on and all that good
No,
stuff.
go for
But yeah, there's a one thing. I have a circle that you can use. I might have mentioned this to you before. I'm not sure. I think I mentioned it to a different student though.
it,
But
maybe.
there's a circle you can use for almost all equations, and that can completely cut out the idea of you having to quote unquote do algebra. So, I know a lot of students take conceptual physics specifically because they need a science, but they don't necessarily like math. So,
Right.
and they're not necessarily skilled at it, but they often are more skilled than they think. I'm slowly pulling this up now.
Well, when I do my lab and she's going over her videos, I'm like, okay, this is like super easy. But then there's just so many formulas for so many different things. And then writing it out differently. I'm like, that just throws me.
Exactly. If you took the time personally to make up a actual, I'm trying to make this thing real quick. If you take the time to make up an actual equation sheet that you found helpful and you
Hmm.
give that to me, I will gladly make a document out of it and make it available to all students as well as you during testing.
Okay. So
So
let me write
just,
it
yeah,
down.
let me know that if you write down any equations like that, I'll be glad to do that for you.
So like an equation spreadsheet.
Yeah, equation spreadsheet. Microsoft Word allows you to write equations really well with the equation editor. So if you might not even be aware that it does that, but you can
No.
do that if you want. And anything you do, I will gladly, unless if there's something specific that I wouldn't normally allow my student to uh, use, then I will check that and knock it out. But I can't imagine you're even going to run across one of those.
Okay.
All right, so I finally got this document open, so I won't screw up everything else. When I make them, I always have to make a duplicate, or I'll end up losing the base sheet that I work on. So here you go.
Okay.
I now have it open. Hopefully, my pen attaches to it immediately. Yeah, it's good. Okay. So one of the things you already ran into, maybe not with reading and stuff like that, but F, which I normally call sigma F, or you see that right there, that sigma
Yeah.
F is equal to mass times acceleration. Now I use that sigma symbol, that Greek symbol I just erased,
Hmm.
which looks like a weird E, if you will. It's the Greek
Yeah.
letter sigma. I use that because in mathematics, that symbol means add up all. So
Yep.
when you say the sum of the forces, that's what we're meaning. And it's technically a vector equation, so it would have little arrows over it, but you're not concerned with that at all. The cool thing is, you see on the left-hand side, you have one concept, the total force, and then
Hmm.
you have equal sign, and then you have two or more factors multiplied. Whenever you have that, you can immediately do something like this. And what I do now is I take the circle, divide it in half. The thing that's by itself on one side,
Hmm.
I put up here, and the one, two, three, or 50 factors that are side by side by side on the other side, I just put right here. So if, for
Hmm.
instance, you're asked to solve for the acceleration, if you look at this circle and cover up the A, do you see
Hmm.
that you'll just have the total force divided by M? It
Yep.
literally looks like that. So that's the formula for it. If you want
Okay.
to solve for M, you cover it up and you see, oh, I'm evidently going to take the total force and divide it by A. And additionally, if you want to solve for the total force, you cover that up. You see, oh, the M and A are next to each other. So that's another indicator that obviously the equation is the summation of forces equals mass times acceleration. But that circle works over and over again. So anytime you have one thing on one side and then a string of factors on the other side, you can always use it. Another example, for instance, would be uh, let's do this circle. And this one might hit a little closer to home given what you just finished covered, but kinetic energy
Hmm.
is equal to 1/2, which you never solve for, but I put it there anyways, mass velocity squared.
Okay.
So you can now, if you want to solve for velocity, you cover it up, and evidently you're going to divide the kinetic energy by 1/2 times mass. You got to use parentheses to do it because they have to stay in the denominator, and math calculators and stuff know, mathematically speaking, when you divide by something, if you're multiplying by something, you have to put both of them next to each other in parentheses for them to stay under the fraction bar. So
Okay.
that'll help. Another one is work is equal to force times distance, and you might even remind yourself that it's that the component of force perpendicular to the distance. distance or displacement vector, or you might put one around there to remind you that you're taking the part of the distance that's parallel to the force, that kind of thing.
Okay.
Okay. Another thing that we need to do is like if you look, for instance, at the equation that this last circle does, that equation is work is equal to force times distance. If you assume that the distance is going to be a constant,
Mhm.
then this is equivalent to work equals a constant times the force. Okay.
Mm.
Whenever you
Yeah.
have an equation that's a constant times something, that's what we call thumbs up. And it means, hey, if the force goes up, the work is going to go up. Not
Right.
only that, it's more mathematical, and this is what conceptual physics are asked a lot of times. If we double the force applied, what happens to the work? W. Well, what this particular equation means is if the force goes up by a factor of two, I write that way,
Hmm.
then the work also goes up by a factor of two. So
Mm.
anytime you have any equation where, A is equal to some constant times B,
Okay.
then if the B goes up, the A goes up by that same factor.
Okay.
But watch this. That's how you handle simple ones where it's like work equals a constant times F. If you did kinetic energy, for instance, which I usually use the symbol K for, as opposed
Mhm.
to writing out the whole word kinetic energy, you know that
Right.
formula is 1/2 mv squared. And they'll ask you questions like, if you're going twice as fast, how much more, or how much is your kinetic energy increased? In that case, you can see this is because they didn't mention the mass changing. This is
Mhm.
just like constant times the square of the velocity. Now, the fact that that exponent is positive or the fact that the velocity is not below a fraction bar, that's what makes it thumbs up, thumbs up. That's why the work equals a constant times F with thumbs up as well.
Okay.
Because if it was something like this, let's say temperature equals K over wavelength, that's a thumbs up, thumbs down for wavelength and temperature. Because
Okay.
one, the left-hand side is in the numerator. You might not see that, but remember, you can always write a number over one, and you see, oh, the t is in the numerator,
Okay.
right? So, so,
Yeah.
so now you see the t is in the numerator,
Okay.
whereas the lambda is in the denominator. That one's what I call thumbs up,
And thumbs down.
thumbs down. Okay.
Okay.
And the big difference,
Okay.
like in this case where I had kinetic energy equals 1/2 mv squared, if the v, I should probably put my pin back on, if the v goes up by a factor of two,
Hmm.
then the kinetic energy, since it's thumbs up, you automatically know the arrow is up.
Okay.
But here's the tricky part. Because of that exponent of two, then k goes up not by two, but by two squared. Uh, this one is a result of that. And this one, this two down here, is a result of what it went up by. So if you double the actual velocity, then that means you put a two down here at the bottom of the arrow. But because the velocity had an exponent of two, you put an exponent of two on that two. So
Okay.
that says kinetic energy went up by a factor of four because two times two is four.
Right.
Okay.
Okay.
And that works other ways as well. For instance, the force of gravity is G m1 m2 over distance squared. So that tells you force and distance are thumbs up, thumbs down. Do you see
Oh,
why?
no, tell me.
Okay. Yeah, no, that's good. I definitely, if there's any ambiguity, I want you to know. So this F
Okay.
is what we're talking about, and this D is what we're talking about. The F is in the numerator, the D is in the denominator.
Okay.
Remember, denominator starts with a D, and so does the word down, so you can use that to remember which one's the denominator and numerator. So whenever the variables on opposite sides of the equals are also on opposite sides of the fraction bar, you get thumbs up, thumbs down, like
Okay.
this. But when they're both on the same side of the fraction bar, you get thumbs up, which is the same thing as thumbs down, thumbs down.
Okay.
So that's the way we think about it.
Will you show me how to write out the equation without the letters?
Yeah,
Or is that
yeah, absolutely. I mean, you can do that, and as well as you can write the equations, or you can just write the circles, or whatever. And you can even put whole words in there. You don't even have to use symbols for it if that makes it more confusing.
okay?
Uh, but let's, for instance, in the case that we're talking about here with the gravity I just gave you, this is a
Mhm.
common formula that happens over and over and over again. What
Okay.
this means is if the distance goes up,
Okay.
then the force, because they're thumbs up, thumbs down, that means the force is going to go down.
Okay.
Okay. Now, if we talk about doubling the distance, the way I'd indicate that is I'd put a 2 down here at the bottom against the exponent. And what that means is I'm going to take the distance I was originally thinking about and make it twice as big. So if it was 100 meters away, now it's going to be 200 meters away.
Okay.
Now, because of that 2, this 2 right here, that means you're going to get a 2 right here as well. That's always the case, no matter if it's squared or cubed or -1 power or -12 power. That number 2 goes down here at the bottom because the number 2 is there.
Okay.
Now, the fact that the exponent of 2 is on the D, that means you have to make that an exponent up here.
Okay.
So if the distance went up by a factor of 2, the force of gravity goes down by a factor of 4.
Oh, that makes sense.
You see now? That's
That's just
why.
like okay.
Yeah,
I
go
think I
ahead.
get the whole like water. So like I
You're
had
thinking
it in
about
my
what's
brain.
above, what's below?
Yes, the force and the upper and lower. Yeah.
Yeah.
Is that
And
like the
it,
same thing?
Yeah, exactly. And
Okay.
that's what you want to think in terms of because mathematically yeah, it's not that easy to understand all this math. But when I give you these little tricks of things like kinetic energy equals 1/2 mv squared, if they're
Yeah.
asking you if you change one thing and they don't say anything about any of the other variables, you just treat all those other variables as a constant, and then you just do what I just did.
All right.
Let me see if you're tracking with this. There is a formula that says the luminosity of the star is equal to sigma epsilon t to the fourth power. Okay, that's just a
Hmm.
formula. You haven't covered it or anything like that, but I think you'll, I think you'll be able to follow what I just did with this. So
Okay.
I'll ask you first: is, or let's say, is L and T thumbs up, or thumbs up, thumbs down? Can you tell?
Up. They're both up.
Exactly, and that's because they're
Okay.
both in the numerator.
Yes.
Yep. Okay, so you know that already.
Okay.
If I increase the temperature by a factor of 2, the luminosity is going to go up or down.
Um,
Remember, the arrow is literally supposed to be thought of as your thumb.
yeah, it's
And
gonna go up.
exactly. Good job.
Okay.
So the thumbs up was the first conclusion you made. And then once you reach that conclusion, then you know the two arrows have to be pointing in the same direction. If you had thumbs up, thumbs down, the two arrows would point in opposite directions.
Right.
Okay. Now
Right.
we know that factor of 2 has to be there. That's what I was showing you with the little purple line
Yeah.
right here. Or excuse me, the
Yeah.
little red line right here.
Okay.
Now, can you guess? Do I need an exponent on that 2 that I wrote down there?
Um,
remember why I put the exponent over here with the purple line. So for instance, in this part, what made me put that exponent of 2 right there? Do you see which?
Yeah, I know. Yeah, I see it.
Okay, so that 2 is what made me put exponent there. Now we're
Okay.
talking just about luminosity and temperature, so we're pretending all this is just a constant.
Okay.
So
So
now, go ahead.
you wouldn't do it because there's no, I don't know. Go ahead, explain it to
Okay.
me.
Okay. No problem. Yeah. So the main thing is what I want you to see is whatever variable we're talking about, if it has an exponent, you've got to put an exponent on that little number.
Right.
So in this case, the exponent is 4.
Okay, that's what I was thinking. I was like, because I saw the four up there, I was like, "Ooh, do I do that four or?"
Yeah, that's exactly what you do. No matter
Okay.
what the equation is, you put a 4, you put a 2, you put a 3, or whatever. Yep.
Okay.
And 2 to the fourth, by the way, is actually equal to 16.
Okay.
So what that means, if you find, and this is a equation we use for stars, for instance, if you found one star had a temperature of 6,000 Kelvin and another star has a temperature of 12,000 Kelvin,
Mm-hmm.
12,000 is twice as big as 6,000. So we know the factor that we're going to put at the bottom of the arrow is 2.
Okay.
But the exponent on the 4 suggests we're going to have to put an exponent of 4 on it. So, in fact, what you can conclude is if you're comparing a star at 6,000 Kelvin and a star at 12,000 Kelvin, the 12,000 Kelvin star is going to be 16 times more luminous. Not 2 times, not 4 times, not 8 times, but 16 times.
Okay.
And that's all because 2 to the fourth means 2 times 2 times 2 times 2. So you see all 4 of them.
So all you did was just like bring that over and bring the four down to get you.
Exactly.
Okay.
Yeah, so that's sort of the trick with this. Let me see with this one. First off, is the summation of the forces. If and let's say an acceleration. If the acceleration goes up, what does the force do? So the first question is it thumbs up, or is it thumbs down for that equation above that, the blue one, F equals ma?
Up and then down.
Okay, the F and the A are up and down, you think?
The A is up,
Hmm.
acceleration, and then the force is down.
Nope, that one's up too, and here's the reason. A is in the numerator and the force is in the numerator.
Okay. Yeah, duh, because they're not. Yep.
Exactly. So since they're on the same side of the fraction bar and opposite sides of the equal sign, that means thumbs up, thumbs up.
Okay.
Okay, so that tells us the total force. If I want to double the acceleration, I need the total force to go up. And in this case, there's no exponent on the A. So if I doubled the acceleration, I would in fact just double the force.
Okay.
So what that means is if you're trying to, push a shopping cart with your daughter in it, and she weighs with the cart weighs 100 pounds. If you now put your bigger son in there and it goes from 100 pounds to 200 pounds, it's going to take you twice as much force.
Okay.
Does
I'm
that
not even
help?
gonna tell you what I was thinking. I was like, oh, the car's driving on the road and then accelerate, but it was coming to a stop. I was confused.
Yeah, yeah. I was trying to say the word cart like a grocery cart, so
Yeah.
that
Yes.
makes it a little different. So just remember the thumbs up, thumbs up. That was one of the things I was talking about. So thumbs up.
Okay. Let me write this down. Thumbs up if it's both in. Up, up.
That means, for instance, I'm just going to make up equation here. Let's say x and y are thumbs up, thumbs up. The way you see that is you should say y is equal to some constant times x. So that's one way you can write thumbs up,
Okay.
and you just verify that the two variables are on opposite sides of the equal sign and on the same sides of the fraction bars.
Okay.
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 So an example would be y equals k times x. Let's say examples. Y equals k times x. Summation forces equals mass times acceleration for uh, the force and for the mass, but it's also true summation forces equals mass times acceleration. It's also true for mass and friction.
Hmm.
And the main reason you can see all that is the variables are on the same side of the fraction bar, but on opposite sides of the equals.
Okay.
Here's another one. L equals epsilon sigma t to the fourth. I'm actually leaving out a factor in there, but it's not a big deal. So again, you see the variable L and the variable T are thumbs up, thumbs up.
Okay.
Now, again, that's just the meaning that the two arrows are a thumbs are both pointing in the same direction. So Y, or let's say if X goes up, then Y goes up. And since there's no exponent, that means the exponent is technically 1. So if you decide to triple x, then you're going to triple y to the 1 power.
Because they're both going up. Yep.
Exactly. And that just means if I went from 2 to 8, or excuse me, from 2 to 6, in my x, or then my y is going to go up by the same factor, 2 to up to 6, which means by a factor of 3. Does that make
Okay.
sense?
Yep.
Now, thumbs up, thumbs down is sort of the same thing. Thumbs up, thumbs down, that means two variables. Uh, crap. Two variables are on opposite sides of equal sign, and, and I should say, I'll do capital and like I did last time, and
Okay.
opposite sides of their fraction bars.
Okay.
And examples for this one is temperature is equal to some constant, or excuse me, yeah, temperature is equal to some constant over wavelength. That's called Wien's law. That's one of the many equations that you learn in thermodynamics, and we know specifically what that constant k is. But the main thing is, if I write k, that normally means, hey, this is a constant. I'm
Oh,
just choosing to write the letter k instead of the word constant this time. Does that make sense?
yes.
So now you see this one is in the numerator, whereas this one's in the denominator. That's what makes it thumbs up, thumbs down.
Yep. Okay.
Oh, and I should say, by the way, on this previous thumbs up, we
Hmm.
had F is equal to G M1 M2 over D squared. So in this case, F and M1 are thumbs up, but
Because there's
not,
a comma.
what's that now?
Oh, because there's a comma.
But it's actually a subscript that's a one on there, but
Oh,
it's on the same side of the fraction bar. The M1 is on the numerator, as is the F. So F
okay,
and M are thumbs up, thumbs up. Not
okay,
only that, if you wanted to consider the other M, then F and M2 is also thumbs up, thumbs up.
okay.
Okay, so that means if you have, for instance, let's say we took the time to calculate the gravitational force that the Earth feels from the sun.
Hmm.
If we now double the mass of the Earth, then it's going to feel twice as much of force. If
Okay,
we double the mass of the sun instead, it's still going to feel double the amount of force.
okay,
If we double both of them, then it's going to be times two, so it'll be literally times four. So if we doubled the mass of the sun and doubled the mass of the Earth, then the force would go up by a factor of four. But it's not because of an exponent; it's because the M1 going up by a factor of two caused it to go up by a factor of two, and then the M2 caused it to go up by another factor of two, and two times two is four.
okay.
Does that make sense?
Yes.
Okay, so there's another equation for thumbs up, thumbs down, but notice the t is in the numerator. I'm talking about this one here. The t is in the numerator, and the lambda, which is the wavelength of light, is in the denominator. That makes it thumbs up, thumbs down.
Okay.
Another equation that's thumbs up, thumbs down is F equals G M1 M2 over D squared, but this time we're just talking about the F, which is in the numerator, and the D, which is in the denominator. So F and D are inversely related, so they're thumbs up, thumbs down.
Okay.
That one's a little more complicated because of that exponent of two, though. So that exponent of two just means the same thing's going to happen that happened with this case right here. Because the velocity went up by a factor of two, that made that two, but because the velocity was squared, that made me put that two there.
Hmm.
Okay, so that's the way we're trying to get you to conceptually think about the physics and stuff of that sort.
Yeah.
Another equation you've done, y'all just did rotational motion, if I remember correctly, right? Wasn't that the last chapter we covered?
Yeah, I think that was lab 7. I'm actually working on my word isn't pulling up. I think I'm working on lab 7
Uh-huh.
right now, or lab 8. Oh, there
Yeah,
it is.
somewhere it should be about week 8 or week 7. So yeah.
Yeah, I think I was getting stumped on the principles on the crown one,
Uh-huh.
the mathematics on that one. I was getting stumped on that one. That's why I haven't
Gotcha.
finished.
Yeah, in the lab when you run it, those are things you don't have any choice. You just have to do calculations. It's not nice
Yeah.
little tricks that I can just pull like this conceptually. But that's the perfect time for you to ask me or Dr. McKay, either one of us. Hey, I don't really think I understand exactly what I'm doing here. Can you help me out?
Yeah.
That's our job. So
Okay.
yeah, if you have any specific calculations, you can just like send me the document that you're working on and maybe highlight the one area of the that you're trying to calculate, and I'll be glad to set up a Zoom meeting with you or send you a photograph of a way of doing the calculation or whatever you want.
Okay. Perfect.
Okay. Oh, I should mention, here's another one that you're familiar with, even though we've already done this equation once, but I want you to remember that this too is a relationship that's thumbs up, thumbs up. So when I say kinetic energy is equal to one half mass times velocity squared,
Hmm.
then the kinetic energy, which is on the numerator,
Hmm.
must be thumbs up with the mass m.
Okay.
So, for instance, this is like going from a Volkswagen Beetle to a F-150. A Volkswagen Beetle probably weighs pretty close to half of what a F-150 does. Because of that, if you had a F-150 and a Volkswagen Beetle both going 60 miles per hour, then you know the kinetic energy in the F-150 is twice as big.
Twice as big. Okay. I
Yep.
was always wondering because that half always threw me off. I'm like, what?
Yeah, the half is just like a constant in this case, as is the v squared.
Okay.
So you can just pretend they're a constant. Don't even worry about the ramifications. All you care about is the thumbs up, or the thumbs up, thumbs down behavior. And
Okay.
this one says if the mass goes up by a factor of two, which that is me saying, hey, I'm no longer thinking about a Volkswagen Beetle. I'm thinking about a F-150.
Okay.
Then the kinetic energy goes up by a factor of two as well. And since the exponent on the m is not seen, it's understood to be one. So you are technically always putting the exponent on the number on the right. It's just
Okay.
usually the number's one, so you don't have to think about it.
Okay. All right.
So yeah,
That,
a F-150 has twice as much kinetic energy as a same
yeah.
speed Volkswagen Beetle.
Okay. I think I get it a little bit.
Okay. We did in kinematics, you also found that the distance traveled was one half AT squared.
Mhm.
So, how do you think time and x are related? Are they thumbs up, thumbs up? Or are they thumbs up, thumbs down? The variables I'm asking again for is x and t. Well, actually, I should probably put them in the opposite order because we normally think of the thing on the right changing. So, t and x. Do you think t and x for this one half x equals one half at squared? Do you think t and x are thumbs up, or thumbs up, thumbs down?
Both of them up.
Exactly. So you see that, and that's because they're both on the numerator of their fractions and they're on opposite sides of the equals. Now, if I double the time, here's the questionable part. What number am I going to put down here?
The two.
Okay, so I'm going to put the 2 there. And what exponent am I going to put here?
The two.
The 2 again. Very good. So we're going to put a 2 there. So that means if the time went up by a factor of 2, then the distance went up by a factor of 4.
Four. So you add it together.
Yeah, it's actually multiplication is what's going on, but it is when you
Okay.
say 4 times, that means adding it 4 times. So it's
Okay.
perfectly
Yeah.
understandable for you to call that adding, but we got to think in terms of multiplication here, or else the equations don't work.
Okay. All
Okay.
right. Yeah.
So yeah, that's the typical problem. For instance, in free fall, when we were studying that, they found that gravitational acceleration is roughly 10 is sort of what they use in the book.
Mhm.
So that formula x equals one half a t squared becomes x equals one half of 10
Okay.
times t squared. Half of 10 is 5, and if you put t equal 1 in there, you see, oh, okay, if I drop an object after 1 second, it will have gone a distance of 5 meters. But
Okay.
now, if I drop the object and allow it to fall for 2 seconds instead, you see instead of 5 meters, it's going to be 4 times 5 meters, which is 20 meters.
Mm.
So that's where all those weird numbers came from when you were
Uh,
doing free fall.
right. And now it all kind of makes sense. Even with the questions, I'm like, okay.
Yeah, that's the kind of questions they're asking you. They don't want you to be able to do algebra. They just want you to use mathematical reasoning, or logical reasoning from a mathematical standpoint,
Right.
to do the work. And that's the questions I try to pick out for you guys, as opposed to a lot of the ones where you're just doing calculations.
Okay. All
So,
right.
with that in mind, here's free fall, just in case you're wondering. Uh, Free fall. Those numbers we had, we're going to say A equals G, which is approximately 10 meters per second every second. Okay. So
Mhm.
at T equals 1 second, X in meters is going to be, we're using this formula right here. So I'm putting the 10 in for A. I
Mhm.
multiply the A by one half, that gives me 5, and then I use the T as it's 1, so it's 5 times 1 times 1. That means my answer is 5.
Okay.
If you go to 2 seconds, then you've doubled time. Okay. And that means, according to this very version that we wrote right here, that means the distance traveled has to go up by a factor of 4. Well, the distance traveled was 5, so now it's going to go up by 4, so it's 5 times 4 is 20.
Okay.
So that's the actual calculus that we're doing there. If you go to 3 seconds, now you've tripled it. Notice I'm still comparing it to the 1 second mark, not to the 2 second mark.
Okay.
So this one corresponds to tripled. Okay. So according to our rule, then the distance traveled is not going to go up by 3. It's going to go up by what? Remember, it has that exponent.
5? Where? Oh, 2.
Yeah, the exponent is 2. So instead of it going up by a factor of 3, which is what we did to the time, we increased it by a factor of 3. The distance is going to go up by 3 squared. And
Okay.
remember,
So
yeah, do you
good.
remember 3 squared is 3 times 3? You see it twice. That's why the exponent's 2.
Yes.
So that means this is going to be 5 times 9, which of course is 45. So that's why they got the 5, the 20, the
Okay.
45, and so on and so forth that you saw in that or that free fall motion stuff.
Okay. So all you would do is change the 2 to a 3, the
It,
threes, if we're going.
exactly.
Okay.
Yeah, you'd say, in this case, you'd say t went up by a factor of 3, therefore x went up by a factor of 3 squared, which equals 9.
Okay.
What would you get if we went to 4.0 seconds? Again, compare it to the first second. What have we done to the time in going from 1 second to 4 second?
What would we change it to?
Yeah, what did we multiply by 1 to get 4?
Oh my God. To 4?
Exactly. So
Yeah.
you take what do you multiply by 1 to get the answer 4?
4.
Yeah, I know it stumps you because it seems like you can't be asking me this stupid question. It's so easy. But yeah, that's exactly it. So it went up by a factor of 4. What that says is t went up by a factor of 4. Therefore, x goes up by a factor of not 4, but 4 squared. And 4 squared is,
Um,
remember, you see
16.
two of them. 16, exactly. So now it's going to be 5 times 16, and 5 times 60 is 5 times 10 is 50, 5 times 6 is 30, so this is 80.
Easy enough. Oh, that's easy.
Yeah, it's what's I mean, once it's been shown to you, it's easy. It's not trivial to come up with it initially, but that's the whole point of, me showing up for you guys to
Yeah.
help you. And the author talks a little bit about that. He just doesn't go in quite as much detail.
Right, right. Yeah. All right, yeah. And then you're gonna post this video if I need to go back and just like,
Absolutely, yeah, yeah.
all right.
This is the first one, so I'm very excited.
Okay,
Actually, I
good.
guess this is the second one, but it's the first one where we did actual science.
Yeah, yeah, I love it. Yeah, because in like 20 minutes, I'll probably forget everything we just did. So I'll have to watch the video.
Yeah, the big thing is, can you try now? What you're going for is trying to make those same, thumbs up, thumbs down assessments of equations. So, uh,
Right.
let's try one more example if you don't mind. Do you have the time?
Yeah. No, go for it.
So one of the equations we learned, this is a little more confusing when I write it initially, but one of the equations we learned is the final velocity is equal to the initial velocity plus AT. That one's too complicated for our conceptual physics, so what we normally do is we pretend you started at rest. If you start at rest, then that means V sub zero, that V with a subscript 0 or O on it, that
Yeah,
means that number's 0. So
that's right. Okay.
if started from rest, then v0, which is the initial velocity, is zero. So I might sometimes write v0, other times I might write vi. They both just mean the initial or the in this case the velocity at time t equals 0 seconds.
Okay.
So if I started from rest, then v0 is zero. So now you get v is equal to at, and I ask you v and t are thumbs up,
Hmm.
thumbs. What are you going to put in that blank?
Up.
Exactly.
Yeah.
Okay. If I triple the time, what's going to happen to the velocity?
It's also going to triple.
Okay, so you say triple, so that means it goes up, and you said triple, so the number is three, and it's
Yep.
specifically since the exponent's one, it's three to the one power, but that's just three. So exactly. Okay. Now let me ask you another one. V and A. Thumbs up, or thumbs up, thumbs down. Sorry about how bad that second U turned out.
It's okay.
So,
Um, both thumbs up.
exactly.
Okay.
TU. Okay, two. So that's how you look at this.
Okay.
Let's try another one. Let's say F is equal to K times X. F and X are what? Thumbs up, or thumbs up, thumbs down?
Both up.
Hmm.
Okay.
Okay, F, or let's do a different one. I'm going to say instead of F, this is an equation that comes up in electricity and magnetism, which we don't normally cover, and I'm not planning on it this time. But this is equal to some constant over the distance. So V and D, thumbs up, or thumbs up, thumbs down?
Up and then down.
Exactly. So this is thumbs up, thumbs down. Uh, let's see if you can follow up on that. If the distance goes up by a factor of 7.4,
Hmm.
what happens to the velocity?
It goes down 7.4
Exactly. So what that means is you're going to divide the old answer by 7.4.
instead of multiply it.
Exactly. That's the only difference here. So this
Okay.
implies divide the first velocity
Hmm.
by 7.4. And I just did a decimal value just so you know. I'm using integers all the time, but it's true for all numbers. So if you increase it by a factor of 3.14159, then you're going to increase the or decrease the other one by a factor of 3.14159.
Okay.
Okay. Anything else?
No, I think that's it.
Okay, if you have any specific problems, like when you start doing practice tests,
Okay.
take a screenshot of them or a photograph with your phone, and send it to me via text, and I'll be glad to help you get through it if you need.
All right, cool. It was super helpful. Thanks so much.
You're welcome. I appreciate you coming.
All right. Yeah.
Yeah, if you don't have any more, then we'll just call it a day.
Yeah. All right. Yeah, that's it.
Okay. Well, thank you. It's Teresa, right? Yeah, Teresa.
Yes.
Oh, and I'm sorry it took so long to get you back in. That's a pain in the butt.
Oh my God, it's okay. It's fine. It all worked out. I'm just glad to be back
Yeah,
in.
yeah, I don't, I hate dropping students, but we're supposed to, so
No, it's okay. It's okay. I could see where you were coming from,
yeah.
so it's totally understandable.
Did
Yeah.
you get that other test made up, the one you missed?
I didn't. It's still locked.
Okay, I thought I unlocked
Yeah.
that, but let me do that right now, and
Okay.
I'll unlock it through till Sunday just to make sure. Is that enough time?
No, yeah, that works.
Okay, as long as that's enough time, then I'll go ahead and do it. I'm going to
Yeah.
do it right now, and of course you're free to go.
All
It
right.
was the online test three, was it, that you missed, or online test two?
I think it was four. I
Oh,
think
you
it was
think it
four.
was four? So none of the above. I gotcha.
Yeah.
I will check that just to make sure, and because I can pull up the grade book and not show it to the world, so that would be helpful.
Okay.
Let's see.
Let me see. I think
Oh,
I'm
there
sorry.
was there was test online test two. You seem to have done online test one,
Let me see.
two. You didn't. You did do three though. That's good. And four you haven't done yet, but I think four is still available till Sunday. So I'm going to go
Uh,
ahead and open up two, and I'll give you till Tuesday just instead. So instead of putting test two until Tuesday, I'm going to make it, I mean, until Sunday, I'm going to make test two due Tuesday because you still already have a test that's supposed to happen by Sunday, and I'll double check that date right now. Yes, online. Oh no, online test for. Oh, that's right. We haven't done it yet. That's why online
okay.
test four is not there. But the practice test is. I'm going to make sure you have practice test two open again. So I'm doing that right now, and I'll have that open until Tuesday, so you'll have plenty of time to get it done.
All right. Cool.
And I'm going to open up the online test too, and it's just for you. I don't know if Canvas will show you a reminder or not, but we want to make sure you check it out soon enough.
Okay. I will.
Okay.
I have off today, so I usually get all my things done today.
Gotcha. Well, thank you, Teresa. I appreciate you coming.
All right. Thanks
And
for
I
your help.
made it due on the 25th at 11:59 p.m.
All right. Perfect. Thank you so much.
You're welcome. Have a good day.
You too. Bye
Bye bye.
bye.
So stop sharing. Bye. Thanks for coming.